Okay, we are going over problem 7.33 at the back of chapter 7. So this is a problem about a bonfire emitting carbon monoxide at a rate of 20 grams per second. It's a clear night, so that's important. And the velocity is 2 meters per second of the wind. If the effective stack height at the fire is 6 meters, what would you expect the ground level carbon monoxide to be 400 meters downwind? So we're just going to focus on part A for this problem. Okay, so we can draw ourselves a little diagram here. It's always a good thing to do. We've got our effective height of 6 meters for our tall bonfire here, and the wind is carrying the plume in this direction, of course. This is the velocity, 2 meters per second, and this is at ground level, so that's the same as UA. UA and UH, effective height, ground height, are the same. So what we need to do is we're going to need to solve for our concentration at ground level. Okay, so that means we're going to need to use equation 7.5, which is a simplification of the earlier equation we're going to use equation 7.49, which is a simplification of 7.45. And let me just pan over here so you can see 7.45. And since it's at ground level, y equals 0, so this last term falls out, and we're left with this equation here. Okay, so we need some constants in our sigma y and sigma z. And we're going to need to know our stability of our atmosphere in order to get those constants. Okay, so for a clear night, and the wind velocity is 2 meters per second at ground level, we need to go over to table 7.7, and we see here for a wind speed of 2, that's going to be this second row here, and we're going to go over to night cloudiness, and the problem said it's a clear night, so we're going to be stability class F. Okay, and so with stability class F, we can get our sigma y and our sigma z here from table 7.9. We need to know where we are downwind. Remember, the problem said 400 meters, so that's going to be 0.4. Okay, so we come across class F, sigma y is 15, sigma z is 7. Okay, and then we insert that into our equation here. So at 400 meters, and our emission rate was 20 grams per second. Let's bring that to, it's kind of a big number, so let's put that into milligrams. And we have our ground level velocity and our sigma y and our sigma z. And times e to the negative effective height, which was 6 meters squared, 2 times 7 meters squared for sigma z. And that gives us a ground level concentration directly downwind of 21 milligrams per cubic meter of carbon monoxide. Okay, so future problem, you might want to convert that to parts per million and compare to what our NAAQS standards are.